For a planar figure, the axis perpendicular to the plane through the center of mass is a principal axis of inertia. 这非常one can easily prove this, because if you choose the plane to be the xy plane, then all particles have zi equal to 0. All the z's are equal to 0. So if you look at the 3 by 3 matrix, the last column and the last row all have 0 except for the diagonal element. So that proves that the z-axis is a principal axis of inertia. Next, we take up the subject of the dynamics of rigid bodies. Now, we already had the formula that the total angular momentum time derivative is equal to summation of the torques. Let us assume V center of mass equal to 0. In other words, we move with the center of mass. So the body then rotates around the center of mass. The angular momentum, we choose the center of mass to be origin. Around the origin, namely the center of mass, there are three principal axes of inertia. So the angular momentum is equal to I1 omega 1 E1 plus I2 omega 2 E2 plus I3 omega 3 E3. E1, E2, E3 are the three unit vectors along the principal axis of inertia. And the angular momentum omega has the components, so omega is equal to omega 1 E1 plus omega 2 E2 plus omega 3 E3. Now when we calculate the derivative, now we want to calculate L dot. L changes with time because omega 1, omega 2, omega 3 change with time. The angular velocities change with time. And E1, E2, E3 also change with time. So let us, for example, ask what is E1 dot. E1 dot is omega cross E1. E1 is a unit vector attached to the rigid body. So the rigid body, when the rigid body rotates, E1 also rotates. And its velocity is the velocity of the end of the E1 is equal to omega cross E1. So now we can calculate L dot. It's equal to I1 omega 1 E1 plus I2 omega 2 E2 plus I3 omega 3 dot E3. That's due to the change of omega 1, omega 2, omega 3. But we also have to add omega 1 times omega cross E1 plus I2 omega 2 omega cross E2 plus I3 omega 3 omega cross E3, because the E's also rotate. But omega cross E1 is equal to omega 1 E1 plus omega 2 E2 plus omega 3 E3 cross E1. E1 cross E1 is 0. E2 cross E1 is minus E3. So we get omega 2 E3 minus plus omega 3 E2. So we substitute that in there, we get L dot is equal to I1 omega 1 dot E1 plus I2 omega 2 E2 plus I3 omega 3 dot E3 plus I1 omega 1 times that. So that's plus I1 omega 1 times this, which is omega 3 E2 minus I1 omega 1 omega 2 E3. I will put that in this row. Then I have I2 omega 2. I get minus I2 omega 2 omega 3 E1 plus I2 omega 2 omega 1 E3. Then I get plus I3 omega 3 omega 2 E1 minus I3 omega 3 omega 2 omega 1 E2. I merely wrote those three terms along this row, along this row, along this row. So, and that's equal to T. The total torque is equal to, total torque is the force, is equal to the time derivative of the angular momentum. So in other words, I have the first component of the torque is equal to the sum of these three terms, is equal to I1 omega 1 dot plus I3 minus I2 times omega 2 omega 3. T2 is equal to I2 omega 2 dot plus I1 minus I2 minus I3. Omega 3, omega 1. T3 is equal to I3 omega 3 dot plus I2 minus I1 omega 1 omega 2. You can also write this in the following fashion. You take this formula plus a cyclic permutation. And cyclic permutation. The other two are cyclic permutations of this one. Now this is a most important formula which governs the rotation of a rigid body around its center of mass. It's nonlinear. Nonlinear in the sense that the equation that we want, the solution we want, is omega 1, omega 2, omega 3 as functions of time. Just like for linear motion, you want v1, v2, v3 as functions of time. But this is a linear. That means omega occurs only once. But here omega occurs twice. So this is a very complicated equation. Whenever you have a nonlinear equation, in general the problem becomes much more complicated. So this is a famous problem in the 19th century. In fact, there was a famous romance in the 19th century. There was a beautiful young woman named Sonia Kovalevsky. She was a Russian woman who lived from 1850 to 1891. In 1888, when she was 38 years old, she won an important French prize. The French Academy wanted to have some mathematical discussion of the solution of this equation. So it was a prize, and she won the prize. In fact, it was a very large amount of money. But she had already been famous before that because she was a brilliant mathematician, and she was one of the very beautiful women in universities at that time. In those days, in Europe as well as in China, women were discriminated against. The Chinese attitude was 女人是祸水. The attitude in Europe was beautiful women are dangerous. But she was a Russian woman, and at the age of 20 she came to Berlin as a student of Weierstrass. Weierstrass was 35 years older than Kovalevsky. And she became his student. Weierstrass at that time was the most important mathematician in Europe. He was extremely famous. He was, for example, the person who really defined what a irrational number was. And he had great contributions to, in fact, all branches of mathematics at that time. So he was a towering figure. And he never married in his life. And here came this young 20-year-old beautiful Russian woman who became his student. But she was not allowed to listen to his lectures because women were not allowed in the lecture halls. So he gave her private letters. So for 4 years, she was his student in this manner. And also they had lots of correspondence. But after she died before he did. After she died, he burned all these letters. So one does not really know the details of their relationship. But there were all kinds of rumors. If you want to read about this, you read. I had mentioned to you earlier that there was a very important book called The Man of Mathematics by Bell, and it has been translated into Chinese, and the book is called 数学精英. That is, I believe, the first book which had a kind of a biography of Weierstrass and Kovalevsky. But in recent years, biography writing about the scientists has become a fashion in America and in Europe. So there has been several books published, both of Weierstrass' biography and of Sonia Kovalevsky's biography. Now let us take the special case of free rigid body. That means the torque is equal to 0 if the body is free. Then we have I1 dot if I multiply this one by omega 1 and multiply this by omega 2 and multiply this by omega 3 and add, I get I1 omega 1 the right hand cancels because every line is proportional to omega 1, omega 2, omega 3, and 6 I terms cancel each other, so therefore it's equal to 0. And this I can integrate, so therefore I get 1/2 of I1 omega 1 dot squared plus I2 omega 2 dot squared plus I3 omega 3 dot squared is equal to a constant. That actually is the conservation of energy. We shall come back to this later. Here we just find a mathematical theorem saying that that expression is, but later on we would come to the realization that that expression in fact is the energy of rotation. So let us take a special case. Special case 1, I1 equal to I2 equal to I3. In that case, you look at these three, because the i's are equal, so this quadratic terms are all 0. So that says omega 1, omega 2, omega 3 are all constants. And that means omega as a vector is a constant, independent of time. So for such a body, when it begins to rotate, it has an axis, and that axis is fixed. It's a very smooth rotation. If you have a sphere, a sphere has I1 equal to I2, I3. It has that property. But not only a sphere, a cube. A cube also has I1, although cube is not spherically symmetrical, but its I1 is equal to I2 is equal to I3. And you can take any axis, you flip it, it will continue to rotate around that axis. Special case 2. I1 is equal to I2 is not equal to I3. Yes, last time we discussed that I1, I2, I3 form a triangle. Now if I1 is equal to I2, not equal to I3, for example, it could be this way, this is I3, or it could be this way. And if it's a cylinder which is very long, it's this way. We said that last time. If it's a cylinder which is like a disc, it's like this. But in both these cases, let's see what's going on with the mathematics. In that case, if you look at the first equation, you get I1 omega 1 dot is equal to 0. You get I2 omega 2 dot is equal to I3 minus I1 omega 1 omega 3. I3 omega 3 dot is equal to the same. Is equal to minus I3 minus I1 omega 1 omega 2. Out of this you get omega 1 is equal to a constant. But omega 2 or omega 1 is a constant. So this omega 1 is a constant. This omega 1 is a constant. Does anybody recognize what should be omega 2 and omega 3? Omega 2 dot is equal to some constant times omega 3. Omega 3 dot is equal to the same constant with a minus sign times omega 2. So that means it's harmonic. Harmonic, that means the sinusoidal functions are harmonic functions of time. In other words, if you take omega 2 second dot, you would get the minus some constant times omega 2. So that means it's a sine wave. So omega 2 and omega 3 goes around the circle. So what happens is that there is a total angular momentum L. L consists E1, has a E1 component, E2 component, E3 component. So let us say that E1 is this is I1 omega 1. This is I1 omega 1 E1. This is I2 omega 2 E2 plus omega 3 E3. Sorry, this is I3 omega 3 E3. Sorry, I'm confusing you. I sometimes call the fixed one omega 1, sometimes call it E3. Okay, let's fix with this. Omega 1 is a constant. So this is I1 omega 1 E1. I'm talking about the case I'm sorry about this confusion. It's I1 not equal to I2 plus I3. This is I1. This is I1. I talk about a case where I1 is different from I2, I3, but I2 and I3 are equal. In that case, I get this. So omega 1 is a constant, and L is equal to I1 omega 1 E1 plus I2 omega 2 E2 plus I2 omega 3 E. So these two form a and the sum of them is equal to L, and L is fixed in space L, because there's no torque. So L dot is equal to 0. So this is fixed. And omega 1 is a numerical constant. So this length is fixed. And this length is also fixed because out of this equation you get omega 1 squared, omega 2 squared plus omega 3 squared is equal to a constant. We had that formula earlier. I1 omega 1 squared plus I2 omega 2 squared plus I3 omega 3 squared is equal to constant. But omega 1 squared itself is a constant. So the 2 and 3 part added together is constant. So we have this formula. So the net result of that is that this length is fixed. This length is fixed. So we have L is fixed in space, but this triangle rotates around L. Is that clear? Everybody happy? Now, where is omega? Omega is not in the same direction as L, because omega is equal to I1 omega 1 plus, so if I draw an omega plot, omega is something like this. Omega is not in the same direction as L. So the net result is there's an L, there's this right angle, and the right angle is making a sinusoidal motion. So it goes around this L axis. But at every moment, the L is not, omega is not parallel to L. If you think about this, what that means is that the body will rotate, but it not only rotates around this it performs a rotation. Think of that body as a plane. A plane body is like this. If it's a plane, then I1 is equal to twice, is equal to I2 plus I3. I1 is equal to I2 plus I3. I1 is equal to twice I2. So that is a special case. In that case, this is L, and this is a plane. The plane is perpendicular to U1, and it rotates. But because omega is not parallel to L, the plane rotates around L, but in the plane, it still rotates inside the plane. So it's a very complicated motion. It's a motion which combines both a rotation of the plane and a rotation inside. Special case 3. I1 is not equal to I2, it's not equal to I3, it's not equal to I1. You can see that this is even more complicated than the second case, and that is the problem on which Madame Kovalevsky won that prize. Next, we talk about rotational energy. Total kinetic energy is equal to kinetic energy of center of mass plus kinetic energy in center of mass. In center of mass system. We have proven this, I think, last week. What is the kinetic energy in center of mass? In center of mass system. It's equal to summation of 1/2 MIVI squared in the center of mass system. That's equal to summation 1/2 summation MI omega cross RI in the or in the center of mass system. Or I write it as 1/2 summation MI omega cross RI dot omega cross RI. Now let's call this A, call this B. Call this whole thing C. Is A cross B dot C. So I can cyclically permute it by a theorem that we had before, and that's equal to summation of MI A cross B dot C is equal to B cross C dot A. So it's equal to RI cross omega cross RI dot omega. So that's equal to 1/2 summation MI of RI squared omega by another theorem minus R dot omega R. omega. Is equal to 1/2 summation mi Ri squared omega minus sorry, I shall write this in the following fashion as 1/2 summation of omega Let's see what I'm doing here. First, Ri squared omega squared, I write it in this fashion. This is a row matrix, this is a column matrix, this Ri squared is a diagonal matrix, all elements of which are Ri squared. And that evident is equal to Ri squared times omega squared. Here, this I write in this form. Omega dot R is this expression. So its square is like this. But because of associative law, I can write this as a matrix. So the net result is that this is equal to 1/2 summation omega I of omega I take out the omega, and this big thing is this, where this thing is equal to Ri squared times the unit matrix minus the column matrix R. But that is exactly J. So therefore this becomes omega J, 1/2 of omega J omega. J is the moment of inertia matrix. If I in particular take the moment, if we take the XYZ axis to be the principal axis, to be the principal axis of inertia around center of mass, then J is diagonal. So then the kinetic energy in center of mass system is equal to 1/2 omega J omega, which is equal to 1/2 I1 omega 1 squared, because this is equal to 1/2 omega 1 omega 2 omega 3 times I1 I2 I3 omega 1 omega 2 omega 3. So therefore it's equal to plus I2 omega 2 square plus I3 omega 3 square. This expression is an old friend. We had seen it just earlier today, but now we know that it has at that time it was a mathematical quantity which we obtained by integration. But now we know that it has a physical meaning. It is in fact the kinetic energy in the center of mass system. So for rotation, I1, I2, I3 play the role of the mass. Omega 1, omega 2, omega 3 play the role of V1, V2, V3. But the mass for the three directions are the same. But for rotation, I1, I2, I3 may not be the same. So it is much more complicated. Okay, now let's work on some examples. Suppose I have a slope with a cylinder which rolls down. Now let's not necessarily have a cylinder. It's a cylindrical, symmetrical body. It could be a cylinder. It could be a Coke bottle. A Coke bottle is cylindrical, but it has a narrow waist. So cylindrical body rolling down. Suppose it has gone down a distance of h. Let's write down it's rolling down, it's no friction. Or rather it's a friction so that there is no heat generated by friction, it's just rolling down. In that case we can have conservation of energy. So the initial energy, we take this to be the base. We take the final position to be the base. So the potential energy is mgh initially. The kinetic energy is 0. So that's the total potential plus kinetic energy initially. What is the final? The final potential energy is 0. The kinetic energy is equal to 1/2 mv squared. We used the theorem we just had proven. The total kinetic energy is equal to the center of mass kinetic energy. This V is the V equal to V center of mass. Plus the rotation energy is 1/2 of, now it's cylindrical and symmetrical, and omega, there's only one omega along this direction. Let's call that direction omega 1. So it has I1 omega 1 squared. No omega 2, no omega 3. It's just a simple rotation. But there's a relationship between the velocity and omega. Velocity is omega times the radius is called r. If it does not slip, then omega has to be equal to this. So we get mgh is equal to 1/2 mv squared plus 1/2 I. Let's just call I. We write that as I. Omega squared is equal to v squared divided by r squared, which is equal to 1/2 mv squared times 1 plus I over mr squared. Which says v squared is equal to 2gh divided by 1 plus Now, in all such problems, if you think about it for a few minutes, you would immediately realize that the force along the direction of motion is a constant. So it is a constant acceleration. For a constant acceleration motion, we have the formula that v squared is equal to 2 times acceleration times the distance. We have used that repeatedly. Suppose this angle is theta. So this distance is d. So d sine theta is equal to h. D sine theta is equal to h. So I substitute that in. I get A is equal to v squared over 2d is equal to g sine theta This formula is in the book. It's equation 12-10. Now, what is the I over R squared? If it is a ring, we are now analyzing the body. If the body is just a thin ring, then the moment of inertia is equal to sum of m times the distance squared. So therefore, it's equal to 1 for thin ring. It's equal to 1/2 for uniform cylinder, circular cylinder. And it's equal to 2/5 for sphere, for uniform sphere. For the same radius, why is the moment of inertia larger for a ring? This is a ring. This is the first case. The second one is 1. The second one is a uniform cylinder, so it's like this. This one is only 1/2. If these two bodies have the same mass and have the same radius, this one has twice the moment of inertia than this one. That's very obvious because the total mass of this is the same as the mass here. So you can make the ring by taking this and expel all the mass inside onto the surface. So this can become this by moving everybody out. If you move something out, its distance from the axis becomes larger. So therefore you increase the moment of inertia. So it's not strange that this has twice the angular, the moment of inertia as this. Now we especially talk about the case of a rigid body around a fixed axis. The accent is on the word fixed axis. Not necessarily through the center of mass. Not necessarily a principal axis. Of inertia. In the last few times, we are concentrating on a general motion. Here we talk about a special case of a motion around some axis. That axis can be any axis, not necessarily through the center of mass, and not necessarily, if it goes through the center of mass, not necessarily an axis, principal axis of inertia. But because it's fixed, so there are some simplicities, and that's why we discussed it. We take origin O to be a point on the axis, on this fixed axis. Usually we take the origin to be the center of mass, but in this case it's more convenient to take it to be on this fixed axis. So you have a certain body, complicated body, and there's an axis. This axis is fixed. It's externally fixed. Now the first point that we discussed before, when we talk about the torque along this axis, this fixed axis, has contribution only from external forces. Need not consider forces due to the axis, due to the axle. It's a complicated body. This is the fixed axis. We had proven this fixed axis, of course, exerts force on the body. But when we consider the torque along the z-axis, we need not consider them. This is a theorem that we had proven before, so don't forget that. Now let us calculate LZ dot. Now LZ is equal to summation MI, because it's a Z component, so it's K dot R cross what is the definition of the angular momentum? Definition of angular momentum is summation for M times R cross B. But the R cross V is equal to this. And we want the Z component, so it's this. Now consider a point. This is the Z-axis. This is the origin. Consider a point Ri. Ri refers to the origin, and the origin is not the center of mass. We don't discuss center of mass at all. We only talk about the origin on the axis. That's what we said before. So this is Ri. And the Ri consists of two parts. We can write it as rho I, consider eta I. We write Ri is equal to rho I plus eta I, where eta I is along the axis, rho I is perpendicular to the axis. So this is the axis, and we have a point, and the rho I is the direct perpendicular to the axis, and eta I is that. So therefore, after you write it this way, it becomes summation mi k dot r is rho plus eta cross omega cross rho plus eta. We write this as A, write this as B, write this as C. Actually, let me backtrack. In order to make it simpler, this is equal to summation. I call this A, this B, this C. So then it becomes summation mi of C omega cross Ri dot A cross B. This is C, A, B. Now, omega cross Ri consists of a rho part and a eta part. The eta part is parallel to omega. So that term, when you cross product two parallel vectors, you get 0. So therefore you can forget about, so this becomes omega cross rho I. Now K cross Ri. K is along the z-axis. Rho I has a rho, R has a rho part and a eta part. The eta part is parallel to K, so you can drop that. So therefore it becomes K cross rho I. In other words, you don't have to deal with eta I at all. You only talk about the vector distance between Ri, between the point in question and the axis, the perpendicular distance rho. Only rho is of any importance. But that is, of course, nothing but mi times summation and rho I squared times omega. So it's I omega, where I is equal to summation mi rho I squared. So for this case, for a fixed axis, you can also define a moment of inertia. This moment of inertia is similar, but the concept is different from what we did before. It's a scalar and is equal to mi times the perpendicular distance to the axis squared. And we have area is equal to I omega. And so I omega dot is equal to torque, external torque along the axis. The book talks about the parallel axis theorem. It's on page 227. If you have a body, here's an axis, here's another axis. Consider two parallel axes. This is the center of mass. Z-axis is through center of mass. Z prime axis is parallel to Z at a distance h. Now we want to calculate the I around the Z prime. That's equal to 1 equal to summation mi. So if this is O, this is the root of the Z prime. Let's call this one O prime. This distance is H. And they have a point here, and let's call this R. So we have R prime. R prime is the R relative to the maybe we should call it the rho, sorry. For our definition, these are called rho. So rho prime is equal to H plus rho. Rho is the perpendicular distance to the center of mass z-axis. Rho prime is the one relative to the z prime axis. So this is equal to rho prime I squared, which is equal to summation mi H plus rho I squared, which is equal to summation mi H squared plus 2 sum mi H dot rho I plus sum of mi rho I squared. So this is I call it Z prime. But this is I around Z by definition. This is equal to sum of the total mass times H squared. What about this one? This one is 0 because H is a constant. It becomes summation mi rho I because the origin, because the z-axis goes through the center of mass. So by the definition of center of mass, this is 0. So we get total mass times H squared that is called the parallel access theorem. For example, if you have a circular cylinder, the moment inertia around the axis is 1/2 mr squared. But if you fix that means the moment inertia around this point. If you now have the fixed axis in here, then it's equal to this plus mass times r squared. So it's equal to 3/2. Now we talk about the kinetic energy of rigid body rotating around the fixed axis. This is trivial if you just calculate it, because every point has a velocity which is omega cross r. So you can easily prove that the kinetic energy is equal to 1/2 of r. The details you can fill in. Okay. We have maybe 20 more minutes. Anybody? I told you that in next Monday's quiz or midterm, there will be no questions which are not in the book. So that's easier for you. So what we have been discussing in the last 2 times, most of it will not be covered by the exam. But part of it is. For example, the parallel access theorem is there. And so you have to decide. You have to look at the book. In the next 20 minutes, I'll answer questions. But by just, if anybody has any questions, which is, first let's talk about questions related to what might become a question in the examination. Anybody has anything which might become a question in the examination? Raise your hand. Also, everybody is very happy. Okay, now, any question. You can now ask questions not related to things covered by the book. But by the way, you will be given the choice of answering either in English or in Chinese or in a mixture. But the questions will all be written in English. There's some, not quite. Some people do not like questions in English. Okay. If a question is a little bit, if a question has unusual English words, we'll give a Chinese translation of it. But most of the questions would be phrased in very easy to understand English, so I'm sure you have no problems. I also want to give you a few tricks about taking examinations. If there are numbers, it is best to first have the form. I told you this once. To first have it in formula, and only in the end do the calculation, because if you don't do that, you sometimes make mistakes of computation, and it becomes very difficult for us to disentangle where your question, where your problems or your mistakes started. And in any case, if your formula is correct, but the final result, the numerical result is not correct, you would get quite a bit of credit anyway. The other thing is that I would advise you to have some scratch paper, 一些稿纸。你这个乱七八糟的东西你就放在稿纸上，不要把乱七八糟的东西放在你的 final paper 上 ，because if you give me 一个考卷是10 pages, I would immediately have an inclination to give it a very low mark. It's best to have a neat paper. How do you have a neat paper? You have some scratch paper on the side. You do those things there and then copy the essence onto the paper that you are going to present. This is a trick about how to get good grades. Also, if you have an important result, to put it in a box so that it's very clear that that is the final result. Write clearly. What else can I tell you? You know that in 科举时代, the handwriting counts in the final grading. Of course, today we don't do that, but nevertheless, a neat paper clearly has an advantage over a messy paper. So remember that. If there are numerical numbers, remember the significant figures statement. So if you get the significant figure very wrong, you'll get some negative points. What else? If you in review, the book in each chapter has a section which is review. If you read those review very carefully, you have more or less understood the respective chapters. Okay, if you have no questions, goodbye and good luck.